Welcome, ladies and gentlemen. Thanks for joining to this lecture called an NMR approach to predict the permeability from NMR T2 relationship and distribution in heavy oil reservoir. My name is Cesar Aguilar. I have been working as a petrophysics since 2005. I would like to thank you to the organization, to the IFEDC Congress, for inviting me to this wonderful event. The agenda will be a short introduction, then the theoretical basis. I would like to go through to the research method and a field application, and finally, conclusion. Let's get started. Machine learning is gaining more and more space in the oil and gas industry. For instance, if you search at one petro, you will find out almost 4,000 articles about this topic. Definitely, it's a hot topic in our industry, isn't it? Today we are going to focus on how neural network approach will help us to improve permeability prediction based on NMR loggings in heavy oil reservoir. A difficult challenge under this difficult environment. 15 minutes is a short time to explain in detail this challenging topic, but I would like to set out the theoretical basis using this illustration combining scanning electrons, microscope photos, and NMR experiments. In the first sample, you will see big pores, low clay volume in this high permeability sample. And if you look the NMR T2 distribution from the NMR experiment, you will see this peak around 50 milliseconds. On the other hand, in this low permeability sample with small pores and high clay volume, restricting the pore through radius, you will see the T2 distribution is shorter than the high permeability sample. This peak is around 18 milliseconds. Then T2 distribution is reduced with small pores, low porosity, and high clay volume. Using the previous knowledge, several correlations has been used to predict permeability based on NMR measurement. For example, the SDR method is based on geometric mean value of T2. Unfortunately, for a structure assuming to be homogeneous in the SDR model is more complex and heterogeneous in most of the reservoir. On the other hand, the Timur model is based on bond fluid saturation and free fluid index in order to predict permeability. But for obtaining this value, T2 cutoff value should be obtained, and this is a very complex and difficult process. But in general, this model failed because NMR relaxation properties of rock sample are dependent on porosity, pore size, and mineralogy, but also in pore fluid properties. And this is very important in heavy oil reservoir because heavy oil decreases T2 distribution, make it shorter, and could be confused with a poor permeability rock. For that reason, we decided to try neural network approach to model permeability. The back-propagation neural network could be used to learn the corresponding relationship between well logging data and core data to determine the implicit non-linear correspondence pattern. In a neural network common architecture, we have the input layer, the log that will be used in the training process. In this case, the entire array T2 distribution in order to minimize the effect of heavy oil of reducing T2 distribution. Because if you use the entire array, the shape of the array also provides important information. The output layer, in this case, core permeability, Rickenberg and Overburden corrected, the hidden layer, in this case 1, and the algorithm will adjust weighting function to minimize error in an iterative process. Our research method starts gathering all the information available. 367 core permeability samples and 34 NMR experiments was gathered in this core wall. Also, we have available a CNR Plus in enhanced precision mode, and we need to process the log in-house. Also, image log, scanning electrons microscope, and core conventional photos was loaded in order to have a robust database. This task is very time consuming, but should be performed in order to obtain accurate results. We want to use NMR experiments in order to optimize simul model parameters for predicting permeability. But you look there, want to put one plot between NMR porosity and traditional core porosity, you will see there is a good match with high correlation coefficient, and the slope of the plot is almost 1. The same occurs with irreducible water saturation derived from NMR compared with irreducible water saturation derived by capillary pressure test. High correlation coefficient and the slope is almost 1. Unfortunately, this doesn't occur with the permeability prediction. The correlation coefficient is very low and the slope is only 0.5. We use the NMR experiment in order to define the T2 cutoff around 70 milliseconds, which is very different from the literature traditional value for our sandstone of only 33 milliseconds. We want to predict permeability from neural network approach. In a commercial software, we build a complete database with gamma ray, XRD data, resistivity measurements, nuclear logs, density, and neutron logs, the T2 distribution from NMR, porosity beams from NMR, the core photos, image log. In red, you will see the neural network predicted permeability, and it does match the permeability measurement from core. The SDR model in green exhibits a poor performance in order to predict permeability. The cause is that the T2 geometric mean value in blue is shorter when the hydrocarbon saturation is high, especially in this zone. The Timur model offers a better performance to predict permeability compared with SDR model, but is poor compared with the neural network approach. Another interval is shown in this figure. In this case, in the low permeability interval in the upper part, the neural network approach honors the core data, but the traditional model estimates a high permeability than the core measurement. The error is high in this interval. When you can observe this one-to-one plot, the neural network approach is capable to reproduce the core data with a slope close to 1, a high correlation coefficient. The performance of SDR model and Timur model are very poor compared with the neural network approach. In terms of correlation coefficient and slope. It is very important to test neural network results using blind data comparison, data that was used during the training process, 83 core samples in this case, and determine if the model could predict permeability accurately in this space. Please observe this untrained interval, highly heterogeneous, with thin beds, sharp permeability change, heterolytic interval, some shells. The neural network approach is capable to reproduce permeability in this very complex interval. The one-to-one plot of the blind core data shows a slope close to 1 and the correlation coefficient of 0.77. Blind data comparison is the most important step to determine if your model reproduces hard data. It doesn't matter if you are using conventional approach or machine learning. Please use blind data comparison in order to determine the model error. With all these results, we can conclude that this methodology yields to improve permeability prediction from 0.45 correlation coefficient with traditional SDR model to almost 0.8 correlation coefficient and a slope of 0.99 with neural network approach in the blind test sample. In this heavy over information, which is very heterogeneous according to core geological information. A robust database with all the geological information available, core photos, image logs, XRD data, and core data provide the best condition to decide if the neural network results are accurate. A domain expert is required to recognize if the automated process honors geological complexity. This workflow is not about maths or a statistical approach or do some clicks. It's about geological comprehension. You need to ensure that your model is capturing all the important aspects that contribute to the fluid flow. That you are capturing your silts, your best permeability intervals, and only this is possible to verify if you have a domain expert validating these important aspects. Thanks for joining to this lecture. I hope you enjoyed it.